Ohm's law is a simple yet very useful relationship between the three fundamental electrical quantities: voltage, current, and resistance. An electrical circuit is formed when a conductive path is created to allow free electrons to move continuously. This continuous movement of free electrons through the conductors of a circuit is called a current and is often referred to in terms of flow, just like the flow of a liquid through a hollow pipe. The force motivating electrons to flow in a circuit is called voltage. Voltage can be thought of as the pressure that pushes electrons through the conductors. Voltage is also a specific measure of potential energy that is always relative between 2 points. When we speak of a certain amount of voltage being present in a circuit, we are referring to the measurement of how much potential energy exists to move electrons from one particular point in that circuit to another particular point. This potential energy is caused by a difference in charge. Without reference to 2 particular points, the term voltage has no meaning. When current is flowing in a circuit, this difference in potential or pressure must be maintained by some kind of pump to move the electrons. Electrons flowing in a circuit can be compared to water flowing through pipes. In this animation we see an electric circuit on the left and a water circuit on the right. The pump is like the voltage source. It pumps from the lower tank to the upper tank, raising the pressure. When the pressure created by the pump is increased, the flow of water increases. In a similar way, when the voltage of the voltage source is higher, the current flow increases. Free electrons tend to move through conductors with some degree of friction or opposition to motion. This creates a pressure drop in a liquid flowing through a pipe. In a similar way, a voltage drop occurs across a resistance in an electrical circuit. When water flows through a pipe or hose, there is a pressure drop from the inlet to the outlet. The longer the pipe, the more total friction. Smaller pipes create more friction than larger pipes. This opposition to motion is more properly called resistance. The amount of current in a circuit depends on the amount of voltage available to motivate the electrons and also the amount of resistance in the circuit to oppose electron flow. Just like voltage, resistance is a quantity relative between 2 points. For this reason, the quantities of voltage and resistance are often stated as being between or across 2 points in a circuit. A unit of measurement is a standardized quantity of a physical property. Units of measurement were among the earliest tools invented by humans. Primitive societies needed rudimentary measures for many tasks: constructing dwellings of an appropriate size and shape, fashioning clothing, or bartering food or raw materials. Units were defined so that people could communicate the magnitude of quantities. For example, one of the units of length was the foot, which was the length of a man's foot, and the inch, which was the length of 3 barley corns placed end to end. To be able to make meaningful statements about electrical quantities in circuits, we need to be able to describe their quantities in the same way that we might quantify mass, temperature, volume, length, or any other kind of physical quantity. For mass, we might use the units of pound or gram. For temperature, we might use degrees Fahrenheit or degrees Celsius. Here are the standard units of measurement for electrical current, voltage, and resistance. The symbol for current is the letter I and is measured in units of amperes. The symbol for amperes is the letter A. The symbol for voltage is the letter E or V and is measured in units of volts. The symbol for volts is the letter V. The symbol for resistance is the letter R and it is measured in units of ohms. The symbol for ohms is the horseshoe-shaped Greek letter omega. Each unit of measurement is named after a famous experimenter in electricity. The amp for the Frenchman André Ampère, the volt after Italian Alessandro Volta, and the ohm after George Simon Ohm. The coulomb is named after Charles Augustin de Coulomb. The mathematical symbol for each quantity is meaningful as well. The R for the resistance and the V for voltage are both self-explanatory, where I for current seems a bit weird. The I is thought to have been meant to represent intensity of electron flow, and the other symbol for voltage, E, stands for electromotive force. From what research I've been able to do, there seems to be some dispute over the meaning of I. The symbols E and V are interchangeable for the most part, although some texts reserve capital letter E to represent voltage across a source such as a battery or generator, and capital letter V to represent voltage across anything else. All these symbols are expressed using capital letters except in cases where the quantity, especially voltage or current, is described in terms of a brief period of time called instantaneous value. For example, the voltage of a battery which is stable over a long period of time will be symbolized with a capital letter E, while the voltage peak of a lightning strike at the very instant it hits a power line would most likely be symbolized with a lowercase letter e or lowercase v to designate that value as being at a single moment in time. This same lowercase convention holds true for current as well. The lowercase letter I represents the current at some instant in time. Most direct currents measurements, however, being stable over time, will be symbolized with capital letters. One foundational unit of electrical measurement, often taught in the beginnings of electronics courses, but used infrequently afterwards, is the unit of a coulomb, which is a measure of electrical charge proportional to the number of electrons in an imbalanced state. 1 coulomb of charge is equal to about 6.25 times 10 raised to the 18th power, or 6 billion electrons. The symbol for electric charge quantity is the capital letter Q, with the unit of coulombs abbreviated by the capital letter C. It so happens that the unit for electron flow, the amp, is equal to 1 coulomb of electrons passing by a given point in a circuit in 1 second of time. And cast in these terms, current is the rate of electric charge motion through a conductor. As stated before, voltage is the measure of potential energy per unit charge available to motivate electrons from one point to another. Before we can precisely define what a volt is, we must understand how to measure the quantity we call potential energy. The general metric unit for energy of any kind is the joule, named after James Joule. It is equal to the amount of work performed by a force of 1 Newton exerted through a motion of 1 meter in the same direction. In British units, this is slightly less than 3/4 of a pound of force exerted over a distance of 1 foot. Put in common terms, it takes about 1 joule of energy to lift 3/4 pound of weight 1 foot off the ground, or to drag something a distance of 1 foot using a parallel pulling force of 3/4 pounds. Defined in these terms, 1 volt is equal to 1 joule of electric potential energy divided by 1 coulomb of charge. Thus, a 9-volt battery releases 9 joules of energy for every coulomb of electrons moved through a circuit. Joules can be electrical heat or mechanical energy. Experiments like this, where a paddle heated up water by stirring it, was performed around 1845 by James Joule. It helped to establish the equivalence of mechanical energy and heat energy. The temperature of the system can be raised either by doing m times g times h of mechanical work on it, where m is the mass, g is the acceleration of gravity, and where h is the distance through which the weight falls, or by adding c multiplied by delta T of heat, where c is the heat capacity of the fluid and where delta T is the change in temperature. In other words, a battery or other electrical power source would do the same amount of work to raise the temperature of the water a given amount, whether it turned the paddle wheel or whether it heated up a resistor to heat the water. The units and symbols for electrical quantities will become very important to know as we begin to explore the relationships between them in circuits. The first and perhaps the most important relationship between current, voltage, and resistance is called Ohm's law, discovered by George Simon Ohm and published in his 1827 paper, The Galvanic Circuit Investigated Mathematically. Ohm's principal discovery was that the amount of electrical current through a metal conductor in a circuit is directly proportional to the voltage impressed across it for any given temperature. Ohm expressed his discovery in the form of a simple equation describing how voltage, current, and resistance interrelate. E equals I times R. In this algebraic expression, voltage E is equal to current I multiplied by resistance R. Using algebra techniques, we can manipulate this equation into 2 variations. Solving for I, we get I equals E divided by R, and for R, respectively, R equals E divided by I. In the next part of this program, we will see how we can use these equations to help us analyze both simple and more complicated circuits.